Yeah, thank you. So if you were not there for the first lecture or if you slept late, there are notes here on my website. In case you have questions, you can either look there or even better ask me. There are not questions. You already had questions about the first lecture. So today I will talk about health and bicombings, which are very useful tools for the study of injective metric spaces and point graphs. So I will first start by stating the existence theorem of an injective hull, which is a beautiful result, an old one, due to Chris Bell in 1964. And so it states that any metric space can be embedded in an injective metric space in a very nice way, in a minimal way. So it's a very useful tool. So I emphasize that it's any metric space X has a unique isometric embedding. So it's a small e from X to a space which I denote E of X into an injective metric space, E of X. So I remind you, injective metric space, what is it? It's a geodesic metric space, such that there was intersecting balls global intersect. That's all you need to remember. Into minimal, I will make it that precise, called the injective hull. So it has other names, injective envelope. This is why the E is for envelope, or tight span. And in fact, tight spans have been studied by computer scientists on graph theory for some times before it came to geometrical theory, as is often the case. The computer scientists are often in a step ahead of us for some aspects, like Shepard's results for median graphs being the same as cat zero field complexes. So we should know about graph theory. So what does it mean that it's minimal? Is that for any isometric embedding of nice metric space X, which is arbitrary into any injective metric space, into an injective metric space Y, there is a unique extension X bar from X, from the injective hull of X into Y isometric embedding. But that the diagram commutes. So here I have F, here I have the embedding into the injective hull, and here I have F bar. Okay. So it's unique and minimal in this sense. Okay. And it's not just the space that's unique, it comes with the embedding. Okay, so this kind of property, you may say, well, what is the use for it? Well, first of all, let's just see what is it in very, very simple and concrete examples. Okay? So first, a stupid remark that if X is injective, then its injective hull is X, right? So most interestingly, if X is a metric space consisting of 2 points, okay, 2-point metric space, and I just have some real number, which is positive real number, which is the distance between A and B. So what do you think is the injective hull of 2 points? Interval. The injective hull is just the interval A and B. And what could be the length of the interval? Because the distance between A and B. For a simple reason. It's the injective hull is quite the most efficient way to fill in the holes of any metric space. So it's give you another point of view of the fact that injective metric spaces are geodesic. It can make any metric space embed canonically in a geodesic metric space this way. If you have 3 points, well, You have a guess as to what the injective of the three-point metric space should be?
Tripod?
Yes, a tripod, exactly. So a tripod, A, B, C. Okay, but what are the length of the legs of the tripod? How do you treat them? Well, there's a canonical way, which is given by the Gromov product. It is half of the distance between AB plus the distance between A and C minus the distance between B and C. And in fact, if you look at this property, it tells you that if you take any 2 points in a space which is already injective, it has a median. Medians exist, but are not unique in injective metric space. So what happens if you take 4 points, right? And this may have less intuitions. I will just tell you the answer. So the generic case would be this shape of a rectangle, if I draw a turn of 45 degrees for some reason. So it does not need to be. With antenna sitting out of each head, with A, B, C, D in some order. And here, what do we have here? Here it's a filled-in rectangle with a specific metric. Which metric? An infinity, of course. And it's an infinity with the standard x-axis and y-axis, which is why I draw it like this. So it looks like a rectangle with antennas with the infinity.
So what happens if your 4 points at a corner is like square with the Euclidean method?
So if I just look at the distance between points. So if you just focus on your space was ABCD, where AB, where this the distance 1, 1, 1, 1, and this is square root of 2. This is a bit more subtle. So here, so it should be one of these kind. Let me see. It should be so. So with the infinity metric like this, it's this distance, 3 times this distance. Okay. So here I have A, and here I have A, sorry, not A. So real number X to be determined. Okay, and I will have here A, E, B, D. And here I have another number Y, which is certainly the same. And you ask that 2y plus x is equal to 1, and 2y plus 2x is equal to square root of 2. And then you solve it. Any other question? Yeah.
I'm confused why we don't get the lateness of median in the 3-point example. If you had 2 medians, couldn't you have 2 extensions? If it's
It's a very good point. It's a very good point. Sorry. Thank you. Thank you very much. There is no uniqueness statement here. The uniqueness statement is only on the space, not about the extension. Thank you very much. And what happens is that if you have 2 injective holes, then there's a canonical isometry between them to meeting with the isometric embedding. Thank you very much. Other questions? Yes?
The most recent example, how does the square embed into that injective space?
So it's not an embedding of the square, it's an embedding of the vertex set. It's just a finite metric space.
But you can fill in the square that has gravity force. There you have it. Always question. You could fill in the square and say, like, where does it go? It probably doesn't go to that.
Well, if you fill in the square, it will be multi-dimensional. The injective will be outward. Yeah. So if you look at these examples, you may say, well, injective spaces looks like cubical spaces, right? Well, fair enough, right? If you want a finite set with 5 points, it's not cubical, right? So there are, I don't know, several combinatorial types, and you can branch along these lines. Essentially, you have branching at 45 degrees. So, as I mentioned, if you try to take the injective of the diagonal space, which is often in L2 metric, the injective of the Euclidean space, well, what you get is infinite dimensional. And if you take the injective of often we say the hexagonal norm, I just draw the uniform, right? In fact, you get off the so this is to emphasize that people who care more about polynomial norms, I think they're quite useful for the study of cell complexes. Any question?
How do you quantify the dimension of the injective space? You say it's
It's a very good point. So I will now give the definition of the combinatorial dimension. Okay.
is span dimensional for a span building?
Depends on the metric.
With the right method?
For most buildings, yes. But for a polyhedron, no. So the combinatorial dimension of a metric space X is the topological dimension. Dimension of its injective code. So maybe combinatorial dimension is not a good name, but it's name that has been good. And it's in this sense, the topological dimension of the injective code is infinite dimensional. And what should you think of as injective metric spaces? Either you're infinite dimensional, or you're a cell complex with piecewise and infinity metric. And then the dimension is the dimension of the cells, which should really be the dimension of the cell complex, if it's finite. That's the most interesting example to have in mind. And this is a very, very weird dimension. I think it's quite powerful, but it's very hard to control. So just from the existence of this injective code, we have that if you take if gamma is a finitely generated group, then gamma acts on any injective code of gamma with the word metric properly. So if you look at proper action on injective metric spaces, you cannot say anything. You should add restrictions on your injective space, either finite dimensionality, which will fail for weird groups here, or properness of your injective space, which will also fail for weird groups here. So this looks like a very abstract result, the existence of the injective code. What can we do with it? Well, it turns out that Long gave a very explicit description of the injective code. So I will do that now. So the description of the injective code. And after that, I will sketch a proof of this result. So the idea is to start with a larger space, which Long calls delta of x, which is a space of all functions from x to r, which are one Lipschitz, and which behaves like the distance through a point, meaning that for all x, y in x, f of x plus f of y is at least the distance between x and y. This is the most interesting of this, the triangle inequality for f as the distance from x to r. And you have an isometric embedding from x into the space delta of x in the subgroup, which to x maps the distance to x. An isometric embedding. So as we will see, delta of x is injective, but it's not minimal. That is the first step. we embed into an injective space, and inside this injective space, we try to find the minimal subspace containing X. And this is the result of Juin. It's an explicit description of this image. Injective of X is the space of all F in delta of X, which are minimal. What does it mean? It means that for the G in delta of X, if G is more than F everywhere, then G is equal to F. Here, inside R to the X, you have something which is bounded below by hyperplanes, and you somehow want to look at the minimal subset. This is what you want. And there's an alternative description of these points in the space of all functions, such that for all X in X, F of X is equal to the supplement over all Y of the distance between F of Y minus F of Y. By this inequality, you know that F of X is always larger than this quantity. But if you want X to be minimal, you want it to be totally the supplement. Okay, is the statement of Planck's theorem here. So I will just explain the main points of the proof. So I do proof. So the first one I can mention is that delta of X will be at infinity distance is injective. It is not much harder than to be that the space of bounded function from X to R is injective with a symmetry, and at infinity space is injective. And the other one is more interesting and a bit more subtle, is that there exists a map from delta of X to this set of E of X, which is the one-matrix refraction, which is equivalent from the isometry group. So essentially, what is the construction of P? Well, you want this formula to hold, so you replace the function F in delta by this formula, that it may not be in delta anymore, so you aggregate it with F, and then you repeat, and you get a decreasing sequence which converges to a minimal point because your reflection. Okay, and now, so P of X is a one-matrix contract of an injective space. So from this we get that P of X is injective. This is quite immediate if you take the definition of injectivity as extension from a one-matrix map from A to X, trying to embed it to extend to a map from E to X. It is unique. And for the linearity, it's not hard. You assume that you have an embedding of P of X into a space Y, and then using properties of injectivity of both P of X and Y, you get a self-map of P of X, which will be the identity. So again, details are in the notes, but they're not extremely hard. So what? Apart from this result, we get a very nice consequence about injective matrix spaces themselves. Any injective matrix space is compatible. So why is that? It's simply because delta of X inside the vector space or X is affine convex. So it's contractible, and P of X is a retract of delta of X, which is contractible. The retract of an affine convex space. Another very nice corollary is that. So I mentioned in my first lecture and again today that injective matrix spaces are geodesic. But there might be a problem of choosing a geodesic, because infinity matrix spaces are not uniquely geodesic. But this provides a way of choosing nicely geodesic. So it's theorem of the but any injective metric space X has a chemical geodesic bicoming. Of course, I will define what it means. So the bicoming is the way to choose geodesics. So what I will call sigma takes as arguments 2 points in the time parameter between 0 and 1 in sense to X. So that I will list the properties we want.
When you're racing, I've been wondering for a while, what long is this? There's many longs.
Force long from BTH to
Yeah.
Okay, so the properties of this bicombing is that we want that this is a geodesic, the map which to T maps sigma of X, Y, T. Well, it is a constant speed geodesic from X to Y. Okay. And we want some nice properties for this bicombing. Chronicality, it's a way to say that geodesics do not diverge. So it's stated in this precise way. For any 2 pairs of points, if I look at X, Y, X prime, and Y prime, and I look at the sigma path between the two, and I will look at sigma of X, Y, T here, and sigma of X prime, Y prime here. I will look at this distance, and we have an inequality, the distance between this geodesic is bounded by an affine function in terms of the initial and final distances. Okay. And the last nice property of sigma is that sigma is invariant, equivalent under the isometry group of X. So there are nice ways to choose geodesics. Yes. It's so yes, it turns out that lungs is also what we call a reversible. That if you swap what X and Y is staying the same. But one crucial property that is not true in general is that it may not be consistent. I will warn you about this. So it's slightly annoying. Sigma may not be consistent. So if you have 2 points X and Y, and you look at sigma of X, Y, and here say you have Z, which is sigma of X, Y, T, then you would like to say that the sigma path between X and Z is the restriction, but it may not. This could be sigma of X, Z. Okay, so this is a problem, because if you want to have arguments using uniqueness of geodesics work in this setting, you certainly want such properties. So it's an open question whether any injective metric space has such a nice bicombing, but at least the common long give us a sufficient condition. Any proper finite dimensional. So these are the 3 important constituents injective metric space. Has a unique consistent bicombing. So I do not write the definition of consistent, it's as you say. So there are 2 important assumptions here. Proper means both compact and finite dimensional. And in fact, proper used to prove the existence of a bicombing, and finite dimensionality used to prove the uniqueness in case of existence of a consistent bicombing. But if you look at groups with geometric actions, you will have such in general. And then it behaves almost like it's a unity geodesic metric space. All arguments you want the thing because of this uniqueness. So I will just take another very nice consequence of the existence of the conical bicombing. So it's a
The envelope of product is the product of the envelopes, so they're infinity method.
yes. If you take a different product, it's quite complicated. Yeah. Even computing the injective hull of say the Cardioc complex with the L1 metric. I believe it's finite dimensional. I believe it's if the Cardioc complex has dimension n, the dimension of the injective hull is 2 to the n minus 1, something like that. So it's
Can't you get like something just by functionality if the enveloping the pattern, like
so no, because so there's no uniqueness in the extension. That's the whole point. And you cannot get the existence of the connected by using that. You need to use if you want connectivity, you need something more than just the universal property. Yes.
so is this the definition of a bicombing or is it a bicombing with different properties?
So geodesic bicombing is this. This is the conicality inequality. Any other question? And this is typical of non-positive curvature because Mark asked what is typical of non-positive curvature is that geodesics diverge. And this is reminiscent of non-positive curvature. So what nice to know just about the essence of a conical bicombing, it's due to danger any injective metric space has isometric inequalities at most Euclidean. Okay, so in particular, if you have a group acting properly for compaction and injective metric space, or even properly for boundary, it has at most Euclidean gain functions. So out effect is not injective, it's not cof-injective, for instance. I don't know why people should study out effect. I don't know. Yeah.
Thanks, I love you too.
You're welcome.
When you say if you have a space with non-quadratic isometric inequality, does it mean that these injective are three-dimensional? Like can I say
It would certainly mean that it's injective, it's an unbounded distance from the starting space, but I don't know what other statement you can have. I don't know.
The standards that most people use, does that mean quadratic or something like that?
So at most quadratic is for the usual isoperimetric inequalities for circles, embedded loops, but you also have for embedded two spheres or higher dimensional questions. Yeah. You have one for each dimension, but the most usual one is for loops. Yeah. Any other question? Okay, so this has been all about injective health of metric spaces. I will now talk about the discrete analog, which is one of Helly. Okay, so there's an analog. So I will now say the results. And connected graph. Okay. Has an isometric embedding. I will also do not but it will be, I will use the name h of x, the fact of the Helly graph, into a unique minimal Helly graph h of x, the Helly hull. You have the same functionality properties as the injective hull does. So when you see this, you may wonder what's the relationship if I take a graph and look at its at its helical. I can also look at its vertex set and look at its injective hole. Well, the two are very closely related. So it's a result by Calota, I will also look at X at the vertex set of X. Then here X, the vertex set of the helical is nothing more than the injective hole of X, which is considered as the space of function from X to R, when I reduce them to the space of function from X to N. Okay, so this has a very explicit description that function, space of function from X to N, that's not for all X, Y, for all X, right? F of X, so now it's the maximum because everything is the distance between X, Y, and F of Y. Okay. So this is just a vertex set. You can also describe the edges with an edge between F and G, F and E. There's anything distance between F and G is equal to 1. Okay, so and just before giving an example, I also make a remark. If you take the injective hole of the helical, it's naturally isometric to the injective hole. Because the graph X fits isometrically inside H of X, it fits isometrically inside P of X. So by uniqueness. And this is a useful remark, in fact. So I will now do an example of such a helical, unless you have questions. Okay, so I will start with the simplest example of a graph which is not Helly, which is the square. So if I represent X inside the space of function from X to N, so what is it? So I will do this in this example. If from X to the space of function from X to N, so A is sent to the function which sends A to 0, B and B to 1, and C to 2. Okay, it's the distance function to A, right? And you may wonder, well, what are other such functions from X to N that satisfy this property? That it's whenever you can also rewrite that as for every X, there is a Y, such that you have f of X that satisfies equal to this distance plus the inequality we had in the graph X. So you see that if you look at F from X to N, which send every A, B, C, and D to 1, the constant function 1 is in the injective hole of X, and it's into the value. Okay. So we can now draw what is the helical. If you have A, B, C, D, it corresponds to a vertex. And what is the distance to that vertex to any other point? 1. Okay, so it's connected to every other vertex. Okay, this is the helical. Okay. This analysis you can do in some simple examples. Okay, and so as an exercise.
So
yes,
how can you tell if you're like you can check it's injective and that's fine. How else would you know that's it? That this is the only time.
This is because it's very elementary. If some coordinate is 0 for a function from X to N, you have no choice, but this is the vertex by minimality. If it's not 0, well, this is a minimal element. So this is it. In this very simple main example, that's sufficient. Otherwise, you need to be a bit more clever. And for instance, if you look at the helical of 5 cycle, or 6 cycle. It's a fun exercise that you may do tomorrow if you wish. And the Haettel of the n cycle is quite several depending on the parity of n.
Would remark also, it seems that the distance cannot, I mean, the function cannot take values more than 2, the diameter of the from
Yes, yes.
just give one.
Any other question? What? Because I look at this function, it takes all points to the value 1. And from this theorem, I see that I have an edge if the distance is 1. So I should put an edge between F and A. So here you should see that if I have a function from x to n, as a function from x to n, its distance to the image of A, sorry, its image of A here is the same as f of A. The distance between f and E of A is f of A. This is a very useful property, so you pass from one to the other. And I use this to say that A and F are distant ones, so I should put an edge between the two. Any other question? Okay, so this remark gives you somewhat a recipe for describing the injective of the graph. Describe the injective of a graph. So what should you do? You should compute the Helly. Well, this is hard in the note, but sometimes you can do it. And then you can describe the injective of the Helly graph. And this has been done by Lang, and I will now explain to you in a minute how you can describe the injective hole of a Helly graph, how to fill in the holes of a Helly graph. Okay. So before that, I need to tell you a bit about how you put metrics on a nice painting. So I will talk a bit about orthospheric metrics. Because when you want to put a metric on a simplicial complex, well, if it's say 2-dimensional, there's no problem. But say you have a 3-dimensional simplicial complex, you want to put a piecewise Euclidean metric. How to choose the Euclidean metric on your 3 simplex? The regular metric is not well behaved. For instance, you can have a Z3 action on such a space. So you need a nice choice of metric on simplices of dimension at 3. So one choice are orthosimplices. So the K orthosimplex is the simplex in R3 with ordered vertices. So here I will add the next one structure of my simplex, that of the total order on its vertices. And here I will have my K plus 1 vertices, V0, which is 0, 0, 0, V1, which is 1, 0, 0, V2, which is 1, 1, 0, 0, up to Vk, which is the vertex which coordinates 1, 1, 1 in R cubic K. What's the feature in dimension 3? So if you have here 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, V2. And here I have 1, 1, 1 in V3. So this is the 3 orthosimplex. Okay. Each time you get distance 1 in a new orthogonal direction. Okay. And you can embed it. So enter it. The LP metric for P. Well, it's interesting to have any value of P. So between 1 and infinity included. So this shape is also what you get if you take the barycentric subdivision of the cube of edge length P. Now, I was talking about simple complexes. So,
Sorry, what did you say about the cube of length?
so if you take a cube of length 2, and you take the first biasynclitic subdivision, it's a subdivision into simple cubes, each of which has this form. Okay. It's only a tilde shape. No, sorry, not a tilde, C tilde. Sorry. Another question? So if P is a poset, its geometric minimization, which I will not see with bars, is obtained. So is first it's a physical complex with vertex set P, whose symmetry are chains of length K, D0, D1. So the poset, you have a geometric realization, which is a simplifier complex. Sometimes it's called the derived complex. And this complex, it's a simplifier complex, but it also has the property that every simplex has a total order on its vertex set. So you can use this metric on each simplex. And go with the left metric associated to the LP auto simplex. I fix the same thing for all simplexes, and I choose this isometry for simplicity. This is called the LP auto spin. Okay. It may sound a bit weird when you see it the first time, but it's actually very general. So you have many examples of such. So what happens if you take very simple posets? You start with P, which is the Boolean poset, which is a set of all subsets of the finite set. Then I will. So if you draw what you have, for instance, for n is equal to 2, here you get the empty set. Here you have 1, 2. Here you have 1. Here you have 2. And here are the order relation. And the LP orthospin metric is just putting right angles and putting this field squared inside R2 with the LP metric. So the Boolean poset gives you the n cube with the natural metric. Okay. Another example, if you take P, which is the poset with 3 elements, well, 5 elements, ABC, which are between 0 and 1, and no relation between AB and C. Then what you get is P will be, you have 0, A1, it's a chain. 0, B1, it's another chain. And 0, C1, it's yet another chain. You get the union of 2 right-angle triangles along their hypotenuse. So, branching of 3 triangles. Another very natural example is that if you take X, a cat-0 cube complex, if you take P, the poset of all cubes of X, right? It's a poset by inclusion, and then P with the LP metric, it's isometric to X with the LP metric up to a factor of 2. Essentially, you pass from, if you had a square, well, you will get the first barycentric cubical barycentric subdivision, and the head length will double, but that's the only thing. So this recovers the standard LP metric on a cat-0 cube complex. Okay. So I insist that this is one of the most efficient ways to put an LP on a simplifier complex if you have some order on your vertices. And now I will come back to my problem of describing the injective hole of a Helly graph. So for this, I need a definition. So, in a graph X, a clique is a complete subgraph, meaning subset that every 2 points are adjacent, and a round clique is a clique which is an intersection of both. And with this definition, I can now give a very precise and explicit description of the injective curve of the Helly graph. If I start with X, the Helly graph. So this description has been carried out by Lang, and I just had essentially a refinement of its construction, which makes it more easy to compute. Itself, I want X to be with finite combinatorial dimension. For instance, locally finite is only degree graph and simple locally. I will look at the percent Px, which is the space of all one clique of X, which is a percent. Okay, by inputting. And now I will describe a new graph. Then the X prime be the graph with vertex set of X prime is the space of set of all one cliques, and an edge between two one cliques A and B inside the space, if one and if they do interest non-trivial. Then the first result is that H prime is a Helly graph, and it has other properties. So there exists the natural map from X to X and where is that? Every vertex is a clique, which is the ball of radius 0. So it depends each vertex itself is a 2 isometric embedding, by which I mean that I multiply distances in graphs by 2. And moreover, this induces an isometry of the factor 2 between the injective force of X and X prime. And now what do I gain with this? And the final thing is that E of X prime is isometric to the L infinity orthosphere realization of the percept X. So I have a very concrete simplicial structure on the injective of X. It is the infinity relation of the percept on a very explicit percept, the percept of all round cliques. In fact, the combinatorial dimension of the Helly graph will be the length of the longest chain of round cliques. Could even be more easy to compute in some examples. Okay, so just before giving a very simple example of application, I will just take the corollary of this result that Helly groups are injective. If you add properly co-compacting in a Helly graph, this you will add properly co-compacting on Px, which is you add properly co-compacting on the geometric realization of this percept. And as promised, I will now give you a very simple example. So if you start with X, which is this graph, okay? A square with a diagonal. Okay, it's a Helly graph, it's not hard to check. So what are the round cliques? So I want complete subgraphs which are intersection of poles, where I do have vertices. I also have ABC, it's the ball of radius 1 second at 8. I also have BCD. And I have also the edge BC, which is the intersection of the ball centered at A and B. And so you may wonder, what's the best way to fill in this metric space? What's the best way to fill in this graph? Well, the injective hole gives you a way to look at this. So you will have here B, A, B, D. Here you will have the vertex ABC, here BCD, and here BC. And what are the edge relations? A is containing ABC. Here we have a two-dimensional chain. Here we have a two-dimensional chain. Here we have a two-dimensional chain. Here as well, with here one-dimensional chain. And you get this here with the right angle as a subset of LEP. This is the best way to fill in this graph. Not the injective hole. Yeah. Proper. No, you do not. If you start with a complete graph, what you get is the tripod. And here you will have the whole thing in the middle. You recover the fact that the injective hole of a complete graph is a star. It's not a clique because A and B are not adjacent. Oh, certainly. Okay. And that's all I wanted to say today. Thank you. Yeah.
You say that sometimes that when you have two injective holes, there is a canonical bijection between them. Let's see why it's canonical. I think there's no uniqueness.
So what I think is that when you have an injective hole here from each line to each line, there's a unique isometry here which makes the triangle unique. This is what I think.
Why is it unique?
It's unique because if you do not, you will have a one-inch self-map in E, which is referred to the identity on the image of X. And it's inside the proof of the fact that the space E of X described by Osman is the minimal injective hole, that if you induce the identity on the image of the embedding, then you are actually the identity. It's not immediate from the definition.
We could take an isometry from X to Y.
Yes.
And the hull of X and the hull of Y.
Yes.
Yeah, you get a map. Is unique or?
It's a good point. It's not unique. Sorry?
It's unique in like the categorical sense.
I'm not sure it's unique because if you take 2 points, you get canonical between them. This is not really unique. So as such, I don't think it's unique. Yes.
The graph isn't itself Helly, but it's universal cover is Helly.
Oh, so it's a very good point. So tomorrow I will talk about local to global properties, both for Helly graphs and injective metric spaces. So it's sufficient to check local conditions. That's it. You will see that.
Thank you.
Thank you.